This is an examination-grade review for the NCAT Aviation Electronics Technician, synthesizing the core principles of resistive components and DC circuit dynamics as they apply to high-reliability aerospace systems.
We begin with component identification. The ability to translate a schematic symbol to its physical counterpart is the absolute bedrock of avionics maintenance. Proper specification is what dictates system reliability.
Proficient diagnostics demand immediate recognition of both the IEEE 315 standard graphic symbols and their physical forms. This runs the gamut from simple fixed-value resistors used for current limiting to potentiometers that function as critical flight deck controls.
Now, standard 4-band identification is simply insufficient for critical applications. The 5- and 6-band codes provide essential data for high-accuracy components. That 5th band adds a third significant digit for precision. The 6th band specifies the temperature coefficient of resistance, or TCR, and the established reliability failure rate. In avionics, both of these are non-negotiable data points.
Component selection is governed by military specifications, MIL-SPECs. Any failure analysis has to account for the failure modes that are endemic to each resistor type. A technician must know that a MIL-PRF 5542 thick film chip is highly susceptible to solder joint fatigue from thermal cycling, a constant stressor in the avionics bay. In the same way, a MIL-PRF 39007 wire-wound resistor is far more vulnerable to internal opens from mechanical vibration.
Let's move to series circuits. Analysis via Kirchhoff's voltage law provides the primary diagnostic framework for validating voltage distribution in single-path systems, like an instrument lighting bus.
Okay, this schematic shows a typical series configuration. Here, current has only one path. Because of that, the total resistance is simply the algebraic sum of all the individual resistances in that loop. KVL is not some abstract theory. It's a fundamental troubleshooting principle. You apply it every day to verify circuit integrity by confirming that the sum of the measured voltage drops across each component equals the source voltage. Any deviation at all signals an anomaly.
A systematic application of Ohm's law and KVL is mandatory. So, step 1, calculate total resistance. That's 22.5 kiloohms. Step 2, calculate total current, which is V over RT. So 45 volts divided by 22.5 kiloohms gives us 2 milliamps. And finally, step 3, calculate the individual voltage drops. The calculated values here, 10, 20, and 15 volts, are precisely what a technician expects to verify with a multimeter.
Now we're going to address parallel circuits. Kirchhoff's current law, or KCL, governs their behavior. And understanding this is mission critical in power distribution architectures that feed multiple line-replaceable units, or LRUs, from a single primary bus. In this parallel topology, the defining characteristic is that voltage is constant across every branch. Total current, however, is the sum of the currents flowing through each individual path. KCL is the essential principle for electrical load analysis. It's how we ensure that the total current drawn by parallel LRUs doesn't exceed the capacity of the primary bus and its circuit protection. Technicians have to be proficient in multiple calculation methods. The reciprocal formula gives you mathematical precision for any combination of resistors. The table method, on the other hand, offers a more efficient, organized approach for on-the-bench calculations, where the values are simpler and clarity is absolutely paramount.
Power dissipation is never a static value. In aerospace, it's a dynamic variable. It's critically dependent on the operational environment, especially the ambient temperature and, most importantly, altitude. This is a classic diagnostic scenario. It requires the technician to calculate the actual power being dissipated by the component to verify if it's operating within its specified thermal limits.
The calculation, using the power formula P equals V times I, so 28 volts multiplied by 0.02 amps, confirms the resistor is dissipating 0.56 watts. This clearly exceeds its 0.5 watt rating, which indicates an imminent thermal failure.
Managing this joule heating requires strict adherence to thermal derating curves. This is a non-negotiable part of avionics design and maintenance, because the lack of air density at high altitude just doesn't provide a sufficient medium for heat transfer.
So, the synthesis of series and parallel principles is demonstrated in complex combination circuits. Understanding this integration is absolutely foundational to troubleshooting nearly all modern aircraft systems.
Troubleshooting complex networks like this one demands a methodical approach.
A technician has to logically isolate and analyze the parallel sections first to find their equivalent resistance. Only then can they analyze the resulting series circuit to determine overall behavior and pinpoint any faults.
These principles aren't abstract theory. They're applied across aircraft systems as defined by the Air Transport Association, or ATA chapters. In ATA 24 electrical power, resistors in a generator control unit's bridge circuit regulate voltage. For ATA 23 communications, precision resistors ensure 50-ohm impedance matching in VHF transceivers. And for safety, a 1 mega-ohm resistor in a technician's grounding strap is mandatory to protect ESD-sensitive components.
This imperative really underscores the direct and unbreakable link between technical proficiency in these electronic fundamentals and the operational safety and airworthiness of the aircraft. Mastery is not optional.